golf tournament. I will mention the golf tournament. Chris and Chris are here, who are arranging our golf tournament for us. Colonial Golf Club this year, June 16th. Registration is live. It is open for registration. Get your teams on now. Eventbrite, you go to the website, the links are there. So check that out. MRO, yes. Everybody knows, hopefully. Who doesn't know that we're having a conference in October? Good. 26th, 27th, workshops and conference, trade show. It's going to be good. We've got a lot of presentations we've been meeting before this to talk about. Everybody else knows about it. So I'm going to get started. We got Ian Watson. You can see him over there. He's actually in Texas. I'm going to have Jared introduce him for us, and then we'll get going.
Okay. Yeah, as Andrew said, we're trying something a little new this year. Good to see everyone out. It's nice to be back in person with everyone, and we appreciate all the support the last 2 years for hanging with us on the online stuff. I know everyone's tired of Teams and webinars and all that stuff, so nice to see everyone in person there. Yeah, like Andrew said, we've got Calgary dialed in today. They'll be watching it live. We've got Ian in Houston, so we are ramping up the tech savviness of this, so this is good. And of course, we upload this onto our YouTube channel, so you can always see this stuff afterwards and share that around, and it's always good information. So without further ado, I'll introduce today's technical session presentation is on pump diffuser failures and solutions. Our presenter up there on the top left is Ian Watson, Regional Retrofit Specialist at Sulzer Pump Services in the US. The technology is available today that allows for the analysis of existing diffuser designs and to provide solutions in the event of a catastrophic failure. The discussions will focus on diffusers, their failure modes, and the parameters to be addressed when retrofitting a diffuser pump with a new diffuser set. A case study will also be presented today by Ian. And a quick background on Ian before I pass it over to him. Ian's worked with centrifugal pumps since 1975 when he joined Weir Pumps, Alloa in Scotland. He has extensive experience in the design of high-energy multi-stage diffuser pumps. Previously, he consulted to the US nuclear industry and presently works for Sulzer as a RES regional retrofit specialist supporting the retrofitting of multiple pump types for greater reliability. So without further ado, I'll pass it over to Ian to give his presentation. Thank you.
Have a good, Andrew. Okay, welcome. As Jared said, my name is Ian Watson. I'm a retrofit specialist with Sulzer, and today we're going to discuss a component known as a diffuser, its function, its failure modes, and centrifugal pumps. Oh, so here we go. I've got this issue again, Andrew, to get forward and back.
Just make sure GoToWebinar is your primary program in the foreground. Yeah, try it now. What do you say? Spacebar? I think we said.
Did
we say spacebar worked?
I did hit spacebar, and it's just going back to that other screen. So hit the control panel.
Mouse around. Oh, there you go. Now you're moving the mouse. I saw it. Try it again. There you go. I think you got control. Yep, you're good. We just got a delay, that's all.
Okay, sorry about that. So today's agenda, we'll discuss Bernoulli's principle very briefly, describe the diffuser, we'll discuss the function of it during operation, we'll discuss some failure modes, and then we'll do a case study. And the case study at the end is pretty good because it shows how you can use today's computer programs to first of all, find the root cause of a problem and how you can also run the program to predict the behavior before manufacturing a new diffuser set, which can be a really expensive project. There's a slight delay here. So Bernoulli's principle. So it's very simply stated that with steady flow rate, the static pressure of a flowing fluid will increase with a reduction in velocity and decrease with an increase in velocity. And as we know in the centrifugal pumps, what we're trying to do is increase the pressure. So if we want to reduce the velocity, then we discuss the equation Q equals AV, where Q is flow rate, A is area, and V is velocity. If we can increase the area, we can reduce the velocity. And by Bernoulli's principle, we will have an increase in static pressure. So that component that provides an increase in area is known as a diffuser. So what is a diffuser? So a diffuser can be described as a set of blades which create divergent passageways rotated around a base circle. And the circular row of blades, obviously, they're connected with a shroud. So divergent passageways will result in the fluid passing through an increasing area. And because of this, the velocity decreases. And as we've just discussed, we will have a rise in pressure. And the element to the diffuser here is known as the throat. And the throat is very important as it controls the flow through the pump. It can actually act like an orifice. Here we can see what's known as a single shrouded open diffuser. You have being open, it's not shrouded on both sides. You can see the blades, you can see the shroud, and you can see the corresponding picture on the right where these vanes are actually milled. And you can have, with an open diffuser, you can have cast or milled vanes. Milled vanes obviously have the advantage. You have equal spacing between vanes. The inlet area to the passageway is equal all the way around. And you have a much better surface finish. Another diffuser type is classed as a double shrouded diffuser. And as you can see here, you can't actually see the vanes because they have a shroud on both sides. Now they're typically cast, but in some cases they're milled vanes, and then you take your second shroud and you milled slots and you lay it down on top and you weld it to the diffuser blade. Now the reason you require double shrouded diffusers in high energy pumps, if it's a high flow pump and the blade is exceptionally wide, you can have high loads on the edge of the blade due to the cantilevered effect. So simply what they do is they just weld another shroud on the opposite side, and that greatly reduces the load. And in the case study, you'll see this was one of the solutions that we looked at, but the manufacturer was going to be a little bit too difficult, and we went with someone else. But you'll see how it greatly reduces the stress on the blades. Now another one, this is called a crossover diffuser, and there's a slight difference here because you can see where the fluid enters the diffuser throat, and then it comes exits the diffuser, and then it runs along these blades into the next impeller eye. And the flow is totally controlled in this crossover passage. In the diffusers we've discussed before, the flow leaves the passageways and crosses over an annulus where it is unguided and then enters the return guide vane. However, on the crossover diffuser, control of the flow is maintained from the minute it leaves one impeller till it enters the eye of the next impeller. So I showed a single shrouded and double shrouded diffuser there on their own, but typically what you'll find is the diffuser it's typically part of a much larger component, and it's typically not on its own. And this is why it's such an expensive item, because once you mill these vanes in here, you have to, you have to basically replace it with a whole casting. So it's a very big, expensive component. Now there is retrofits available where you can take off the blades on one component and reset a new set of blades for a different design. But basically the diffuser is a much bigger component than just the diffuser itself. So what's a function of a diffuser during operation? So if we look at the location of a diffuser, and you can see here are the impellers in the multi-stage pump. There's 1, 2, 3, 4, 5. And the diffuser sits right above the impellers. And like I was talking earlier, when I said that the diffusers are part of a bigger component, you can see this whole component here is a diffuser. So replacement of that is very expensive. So if you go into a modification, you want to make sure that the new design is run through a computer analysis prior to proceeding. So flow through the diffuser. So the diffuser is positioned around the impeller. The exit center line of the impeller and diffuser have to be aligned. Flow exits the impeller and enters the throat of a diffuser. It's a stationary component. As the flow goes through it, its velocity is reduced and its pressure increases. And then as the flow leaves the diffuser, it's directed to the eye of the next impeller by what are known as return guide vanes. These vanes are designed to remove the swirl and guide the fluid in the radial direction to the next impeller eye. So failure modes. What causes a diffuser to fail? And this is just my own opinion here, that there's basically 3 categories, right? It can be caused by the design of the diffuser itself. It can be caused by operations, plant operators. Or it can be caused by poor shop practices during the repair and assembly of an element. If we look at the design of a diffuser, this is what you don't want. You don't want a knife edge. You don't want blades that are too thin. You don't want a small nose radius. Too small a root radius between the diffuser blade and the shroud that you can see here. And what happens here is you just end up with cracks. And you can see this picture right here. This is the result of this, is breakage. And what you really need is a nice radius between the diffuser blade and the shroud and the nose radius for entry to the diffuser. This is what you don't want. The design of the diffuser, when you talk about poor hydraulic design ratios, now these ratios here, you have the diameter here, D1 and D2. In between there you have a length, the length of diffusion of the diffuser. So basically the length should be 3 to 3.54 times D1, and D2 should be about 1.4 to 1.6 times D1. So these are not, these ratios are not cast in stone, but if you're looking at your diffuser being modified, these are numbers that you should keep in mind, because they're typically the industry average. I mean, you don't want anything below this, because if you do, what happens is you don't have enough pressure recovery in the diffuser, and you put the pump back in service and it doesn't perform its function, because these ratios are all off. The other one here, which is a big one in the industry, is gap B. And that's the radial gap between the OD of the impeller blade and the ID of a diffuser blade. And over the years, as energy levels picked up, there has been multiple failures of diffuser blades because of this gap. And I would say maybe 40, 50 years ago, they tried to make this gap as small as possible. And it helped the efficiency. And then when the energy levels went way up, as the impeller came by the diffuser blade, there was such a pulse that it was causing catastrophic failures. And this gap is known as gap B. The desired gap B in a diffuser pump is maybe between 4 and 6%, but sometimes it can be higher, but you don't want it much lower than 4. And how do you identify this gap? So if you're taking vibration on a multi-stage pump, and you have a vibration, say, at 6 times running speed, and you happen to find out you have 6 impellers, then you have a vane passing problem. Almost certainly you have a vane passing problem. Now, the ways to eliminate it is you may want to change to a 7 vane. This is when I'll talk about natural frequency in a little minute. But this vane passing can cause catastrophic failure, and especially when it matches the natural frequency of the pump's head or bearing housing, support bracket, base plate, or piping. And this is when you have a resonance condition. Sometimes the vane pass itself will be so high that you need a brand new diffuser set. But if you have a structural resonance, then you have a major problem. You may have to detune the drip pocket bearing housing to get away from the excitation, or you may have to change the number of impeller vanes to get it away from the natural frequency of the pump structure. Failure modes caused by plant operators. Obviously, the angle of flow coming out the impeller matches the diffuser. And if you want to take your pump back and run it at 50, 60%, 40% of BEP, then these angles don't match anymore. And you end up with stalled areas in the diffuser. You have reverse flow, you have erosion, the blade weakens, and then it breaks. So failure modes caused by poor shop practices. So one of them I've always found is welding of existing diffuser vanes with non-qualified procedures. No post-weld heat treat and no hardness checks. Vanes come in, people weld them, and they grind them, and they put them back in service, and then they break and they come back in. That's typically what happens. Another one is when you cut back the existing diffuser tips, resulting in unacceptable diffuser ratios. And I know it happens where a plant may get a diffuser blade in, like on the left-hand side here. And what's the obvious fix, right? It's to take a grinding wheel, grind off the damaged area, put in a nice nose radius, and put it back in service. Well, guess what? You just ruined your ratios. And it's quite possible the pump would totally fail in operation. It wouldn't produce any head because there would be no pressure recovery in the diffuser section. So something to watch for. If you have vane pass, if you have broken tips, if you have eroded tips, it's not just a case of cutting them back. You have to ensure that you still maintain some good diffuser ratios during that repair. This next one here is when you get a multi-stage pump. We've seen it before, and these faces in here don't look too good. So what do? They set them up and machine them. As you machine them, you obviously have to machine this as well, right? Because if you didn't, then this would crash into here. But what happens is all the covers start moving to the left. So if you take 5,000 from each surface, all of the time on a 10-stage pump, you're back here, you've moved the diffuser center line in about 67 thousandths. But if you don't address this by modifying the split rings, by machining them so you can move the impellers forward, then you have a total misalignment of the impeller blade to the diffuser blade. So that's another thing to look out for when the pump's in the shop getting repaired. You want to make sure you don't just cut diffusers, lose your ratios, and you don't want to skim surfaces, creating a misalignment, actual misalignment within the pump itself. And this is what we want here on the right. And typically, you know, the problem here with diffuser pumps is, in a multi-stage pump, the width of the diffuser is not much wider than the impeller. If this is a volute pump, you don't have that problem because the entrance to the volute is way wider than the impeller. But in a diffuser pump, care has to be taken for this axial alignment. And you can see what happens on the left-hand side here. You end up with misalignment, you have turbulence and efficiency, and it's something that you don't want after a pump repair. So the case study, this is a major refinery in the US, and we received the pump in-house, and as you can see, it was not in good shape. We had multiple catastrophic blade failures on multiple stages. So the problem here, when I first looked at this, I said there's two issues. Was the loads too high, where it just snapped off the blade, or was there erosion prior to the blade snapping off? The erosion may have weakened the blade, and then a load that wasn't too high might have been enough to take it from service. So due to the fact we had multiple blade failures, multiple stages, simply reverse engineering the diffusers and manufacturing was out of the question. We had to find the root cause. So the decision was made to scan the existing blade. We found one or two good blades, created a solid model, and we sent that to the advanced engineering group. And the question I said earlier, did the erosion cause the blade to weaken, or were the loads simply too high? At this point, we decided to test the pump at 80% of BEP, right on BEP, and a flow rate of 120%. The 120% was to, just in case for the future, if the plant wanted to increase the flow, we would know if the diffuser was good for that. This here was the input that was used for the computer program, which was used from our model. You can see the impeller section here shown in gold, and the diffuser section shown in green. This is this crossover I was talking about earlier, where there's no blading. It's just a crossover area. The return guide vanes, impeller, diffuser, return guide vanes, and we use a two-stage model here for analysis. And as you can see here, we took multiple pressure points. You can kind of see the small white dots here. This is an impeller in light green, and in the diffuser here, you can see the diffuser passageways. You got right here, here, and here. We took all these pressure points. So there was two things to look at here. There was the flow through the diffuser itself and the loading on the blades. And we started off with the CRT. So what were we looking for? If you look at this picture, you can see this word in here called stall, right? And it's white, which basically means there's no flow through that diffuser passageway. And that's what we were looking for in the results when we performed the analysis on our pump. And here was the best efficiency point flow rate, and you can see we have a nice set of colors here. There's not any diffuser stall, and everything looks pretty good. We then go to 80% of BEP. Everything looks pretty good again. We're quite happy with it. You can see a slight separation here on the non-pressure side, just beginning. And I'd imagine if we took this down to 40, 50%, this would probably be a lot worse. But we're quite happy with that. And then at 120, you can see we have you see a little bit of higher velocity coming in here with the yellow, because we're up 120% BEP. But once again, the flow through the diffuser is all, we're happy with that flow. So there's no real problems with the flow through the diffuser channels. So the next thing we had to check was the pressure pulsations. And what are we looking for? And our advanced engineering group has done multiple studies of diffusers, and they found that in diffuser throw, they need to keep this below 0.05 minus 0.05, or 0.05 and 0.06 for safe operation. And that was it at BEP. So we did an analysis, and as you can see, Q equals 1, which is the best efficiency point, the pressure pulsations are already way above what we expected them to be. we then go to 120. Now, you remember I said that wanted to take a look at this to see if the customer could increase his flow rate. Well, this would be the results of increasing the flow rate, and unfortunately, they couldn't give us the flow rate for each pump. They could only give us total flow, and I suspect that this plant was operating in this region because the pressure pulsations are way above what they should be, twice what they should be. And then we come down to 80%, and you can see they're still above the recommendations. So we have a problem here that we're creating too high a pressure pulsation between the impeller and the diffuser. Come on. So if you look at a result summary, we have flow channels which are really good, and we have pressure pulsations that are too high. So how do you do that? How do you solve this problem, right? It's basically that you want a brand new diffuser set. Can you trim back the diffuser? Can you trim the impeller? There's a few things you can do. Well, number one, we can't trim the impeller. It's they need the head out the pump that they have. And number two, we're kind of stuck with radial. Well, here's kind of something. So we need to increase the B gap between the impeller blade and inlet tip to diffuser, recommended 5%. But we have a problem with this pump design because we don't have any radial height. If we make the inlet to the diffuser bigger, then to maintain those ratios I'm talking about, we need the OD to be bigger. And because of the design of this pump, we can't do that. So we're in a kind of bind. And we decided that what we can do is, oh, no, I'll just go back here. Now, remember I was telling you we can't, if we were to increase this here, we would have to increase the OD. And if we increase the OD, then we're blocking the flow to the return guide vane. So, kind of innovative solution, we increase the blade count. And by increasing the blade count, you can increase the base circle, which gives you a bigger B gap, and therefore the vane tip-to-tip diameter. The large number of vanes allow us to reduce the inlet diameter of the throat. And the diffuser ratios, which are based on the inlet diameter, can now be met, and the new diffuser design can be inserted within the confines of the existing diffuser. So the proposed new diffuser was analysed and indicated the pulsations to be greatly reduced. And this is the new design with the 12 vanes. You can see here we managed to maintain a L over D1 of 3.05 and a D2 over D1 of 1.73. So by going to 12 vanes, we're able to go to a smaller throat and maintain the ratios for good hydraulic performance. So I've actually got two slides that are kind of duplicated, but we'll go through this one. So the diffuser vanes experience a static loading, resulting in an average stress and dynamic loading. And the allowable is set typically at 70 newtons per millimeter squared. For the original design, we were getting a value of about 64.2 with an open diffuser. So with such a level of dynamic loading, a closed diffuser blade would have been selected if we could not increase the B gap. So if we were unable to increase the gap between impeller and diffuser, we could have went to the double shrouded. If you remember, I was talking about the double shrouded when you have high loads. This would have been the thing that we could have done. However, we decided to blend around the blade. The radius around the blade are too small. We need to increase them. It's a nose radius. The diffuser loading could have come down to 10.7 with a double shrouded, but the fact that we can increase the B gap from 3.2 to 5 and increase the leading edge thickness from 3 to 4.5 millimeters, the loading would decrease to 23 newtons per millimeter squared. So basically, we've reduced the load to 30% of what we had in the past by being able to increase the B gap between the impeller and the diffuser, by putting in a nose radius, and by putting in a large radius between the shroud and the diffuser blade. And here you can see the original pulsations in blue, and the modified pulsations in orange, for a flow rate of 80%. And this is the flow at 100%. They're also greatly reduced, and they're reduced at 120, but I don't think I have the graph for that. So just like summary, diffuser blades will experience an average load of 64.2. If we go to double shroud, we can go down to 10.7. If we increase the B gap, we go to 23 newtons per milliliter squared. And by a thicker nose radius, big root radius between diffuser and shroud, we have a solution to our problem. And that's actually what we did. And the pumps are in, and they're running really, really well. But a question here is, what if the pump was running back in its curve? Say 50, 60% of BEP. So if you're running back here, and you only need the same head, say at 4,000 feet, right? Then you would hit this point, but you can trim the impellers and hit this point without any problem, depending on what head is required. But when you do trim the impellers, right, you've got an efficiency point, an original BEP of 100. But always remember, there's an option to move the efficiency curve back to match the new flow rate, if in fact you're operating at a low flow. And the only reason I want to show this is to put some numbers to it to see how much money we're talking about when moving the BEP. Here. So with a flow rate of 1,800 and head of 4,000 feet and 82 efficiency, that's the cost to run the pump for a year. 8,400 hours at 10 cents a kilowatt hour. And then if you run it at 1,000 gallons at 5,300 with 60% efficiency, it costs you this much, right? But if you can move the efficiency point to the left to match the new flow rate, it only costs you this. And that's a savings of $600,000 by making that modification. And that pays for a new rotor in 6 months. So I just wanted to show you the numbers that can be attributed to moving the best efficiency point left and right on high energy diffuser pumps. And I think that's the last slide of the presentation. Okay, so thank you. That's the presentation ended.
Okay, thank you very much, Ian. That was excellent. We'll move to the Q&A part. We got food coming out in 20, so I hope you guys got 20 minutes worth of questions. No? Ian did that good of a job? You have no questions? Was very good.
I guess I can go have a beer now.
Yes, join us.
You know, I was going to wear my Chicago Blackhawks hat there just for all you guys up in Canada, but I never bothered.
Hey, Ian, I just thought of a question for you. So you were talking about going to a double shroud, right, to have a little more stability potentially?
Yep.
Now, wouldn't that reduce the amount of flow that you'd be able to get through there?
No, because the shroud is added beyond the width of a diffuser blade. What you would do is, let me see here.
And the double shrouded, I mean, I'm assuming you're going to have less recirculation, right?
Yeah, the double shrouded is, let me see. let me see here. We'll come back. Now, what you would do was you would machine the cover, the preceding cover. I'll show you. Could be the
You're
next
looking
slide.
at sectional.
Yeah, I'll get it's coming up here, I think. I think it was the last one before the case study. Yeah, here. So see here. So just say you wanted to double shroud this diffuser, right? Then that double shroud would go right here, and you would just machine into this cover, like if it was a 1/4 inch shroud, you would just machine into the cover by 1/4 of an inch, and then the double shroud would take up that space that was already machined in there. And I've seen diffusers, separate double shrouded diffusers used in high erosion pumps, and they put gaskets in there, and this is pumps that eroded really quickly. And what they would do is, instead of having to make the whole cover, they would just use a double shrouded separate diffuser with 2 gaskets. And then every year, they would have a new set of diffuser blades ready. They would just take the pump apart, throw the diffusers away, put on the new diffusers, and they'd be in operation really quick.
All right, somebody in the crowds must have some horror stories or something. Things that they've seen out in the field.
I'm sure.
Come on, Brandon, share us the story. You're not allowed to? You want to know how hard it is? From, I guess, finding the problem, I guess, knowing that you have a flow problem or I guess a different condition you want to meet. I guess you contact Sulzer Engineering, right? So they'll figure it out for you.
Yeah, I mean, probably there's a lot of people who don't know Andrew, but I remember I was working at IDP back in the day, and this was a big thing in America because EPRI put out a thing for everybody to bid on. It was the guidelines for high energy boiler feed pumps, and I don't think American companies bid on Sulzer. Sulzer bid on the project, and they won it. And all the stuff was performed in Switzerland, believe it or not. So they are a kind of high-tech diffuser company. Although, you know, they purchased Bingham have a lot of loop pumps, but they are really high-end in the diffuser style of the business, and they're expensive items. I mean, if you make a brand new diffuser set, right, and you know the pressure recovery is a mile off, and I mean that's you just can't afford to do that.
All right, it makes sense to me. So I guess we're still waiting for food here. They're not going to show up until 6:30 or so, I think. So you got some, you got to tell some stories or something. I think maybe the Calgary guys want to say hi.
Hello from Calgary. Yeah, no, pizza was on happy hour, so I had to get it on order before it got more expensive.
Okay, we got a question here from a former presenter, Mario Fortunato. Ian, can you comment on the amount of computing resources needed to do these simulations?
I think we use ANSYS as one of the programs we use. This was sent to Switzerland, so I'm not sure what else they use, but they have a lot of data because they've designed a lot of diffusers. So I don't know if they've written their own software. It's quite possible, but I mean there are places you can go, right, that can do this analysis. It's just, you know, CFD, FEA. I mean there's a lot of companies can do it, but having the knowledge of the internals of the pump is also advantageous, right? There's other things that, you know, I never spoke about here, like the for instance, this gap here between the shroud, the OD of the shroud of the impeller and the cover. Now, that there acts as an orifice for the leakage coming down here and then leaking by the wear ring, right? So if you don't have the proper gap here and you go back on flow, then the fluid comes in here and it starts circulating, right? So when you get a higher velocity circulating fluid than you have on the other side, then the pressure drops. So that effect, so instead of having, I mean, if you take discharge pressure in here and discharge pressure from here up in this slot, you have an unbalanced thrust, right? Because you've only got suction pressure here and discharge below this line here. But once you start having flow disturbances in here, it can break an impeller in two without any problem. It can snap the shroud. So there's a little gap in here called the A gap, what I didn't touch on, and that's typically 30 to 40 thou, and the length of it should be maybe 120. And that streamlines the flow into the area at the back of the impellers, and that's a critical thing too, because as I say, it affects the thrust, and you get thrust reversals, and I've seen shrouds that have been absolutely snapped in two because of that. So, you know, it's like when I was talking about the axial misalignment, and I showed that picture. Who was it? See, if you have this misaligned, see this gap here, that'd be way too big, right? So flow comes down here, comes in here, and then goes through the wear rings and comes back around. That's the leakage flow. So typically you have this is only 30 thou in here. So if you have disturbances in here, this orifice can streamline it. I mean, if you have it coming down here and it's all over the place, then you have axial. If you have axial vibration in the pump, it is back on the curve. Then this is probably one of the reasons. You're called your A gap. I spoke about the B gap because I was talking about radial vibration, but your A gap might be ineffective.
Any other questions for Ian before we wrap it? That's half a hand there, Dave. No. Okay. No. And if anyone thinks of anything, feel free to continue the conversation on LinkedIn. We've always got our page active, so I know lots of folks here are following that. Please do. We'll post this on YouTube as well.
All right, we got one question from Calgary though. Hold on. We got a really good one. We'd love to talk to Ian about it.
Excellent. Fire away.
So Ian, does Sulzer recommend a wear solution on the static components, or do they prefer using cavitational resistant materials?
Go through that. You mean cavitation for castings?
Well,
Either coatings or the static materials built into it.
So we're talking about cavitation issues here.
Yeah, wear solutions.
Yeah, wear solutions for cavitation.
So Ian, do you use, for example, on your diffusers, would you prefer using like a CA6&M, which is cavitational resistant stainless?
Yes.
Or on factory, do you guys recommend a wear solution on static parts?
Well, you can weld. I mean, you can spray if you want to, but CA6&M is a good material. I mean, it depends on the corrosion resistance. Sometimes you'll have to make it a 300, depending on what it's used for, right? But certainly, you can spray overlay in diffuser blades and some rough surfaces. Yeah, definitely. Because sometimes CA6&M won't be good enough. CA6&M is great for weld repair, but sometimes a spray with stellite or some other material could be good.
Great question, Derek. Thanks, Ian.
Okay, that's all from Calgary for questions there. Okay. Okay.
Okay, yeah, we'll wrap it up. So again, thank you to everybody in Calgary. Thank everybody here in Polo Social Lounge in Short Park. It's been great to see you back again. We were supposed to have, it was March 2020 that got canceled. And so anyways, it's been since January since we've seen each other. We missed 2 golf tournaments. We missed 1 MRO. And we're going to make up all for that in 2022. All right. Thanks very much, everybody.
Thank you.